William Thomson, better known as Lord Kelvin, was born 200 years ago. And pioneer in physics, he would go on to make key discoveries in thermometry and electromagnetism. And later in his life, he would become an inventor, making him one of the most important figures of the 19th century. And here to tell his story is Graham Machin, a senior NPL fellow with over 30 years of experience in the field of thermometry research. He is a visiting professor at Birmingham, Glasgow, and Strathclyde universities, and is a fellow of the Royal Academy of Engineering and was awarded the Hartley Medal and has been president of the Institute of Measurement and Control. His research interests include future Kelvin, thermometry, and he leads the NPL's metrology activity for nuclear decommissioning. And we would also love to encourage your participation in the talk. So up on the screen is a QR code for Slido. If you scan the QR code or go onto the website and enter the code, you can submit any questions during the talk. If you're not comfortable using that, we also have a microphone running around. So if you stick your hand up at the end of the talk, we'll answer any questions as well. And I will now pass you on to Graham. Thank you.
So is that working? It's working. Yeah. Okay. Well, it's really great to be back in Orkney. Always love coming here, enjoying the weather, um, and uh, and just a very warm welcome that I get here. And I really thank Howie for inviting me to speak. I was asked to speak about the life of Lord Kelvin, actually by the MPL outreach team. They said, "Oh, it's 200 years since the birth of Lord Kelvin," and they said, "Oh, you're lead the transformation MPL. You should know everything about him already, so it should be easy for you to write that talk." Well, they were right and they were wrong. Anyway, I'll explain that in a minute. So this is the sort of an outline of my talk. I'm going to give a little bit of introduction, then talk about his biography, talk about a few of his significant scientific activities. He revolutionized academic life throughout Great Britain and wider afield. He with Clausius, invented thermodynamics, and he really was very keen to put theory into practice. And there's a thread running through my talk about that as well. And then because I work at the National Physical Laboratory, I want to speak about some of his contributions to measurement and the metric system and MPL, and then a few fun facts about him. Well, I think they're fun facts about him at the end. So as I say, when they asked me to speak about the bicentenary of his birth, I thought, oh yeah, his main contributions were really to about temperature in the 1840s. What could go wrong? But when I scratched the surface, I found an amazing life, an amazing person. He was a scientific genius of the absolute first order. And when you found out how much was written about him, there was an obituary in the Royal Society just after he died. It was over 100 pages. Who gets an obituary of 100 pages? Just amazing, uh, amazing. And I've never seen an obituary with equations in apart from the one in the Royal Society. And his first biography was this massive tome of over 1,000 pages, giving a almost a blow-by-blow account of his life. And then there's lots of books written about his life as well, which I hadn't realised. And then this, as well as that, there's vast stores of original material at Glasgow, in Cambridge, and at Royal Society. Just vast amounts, which I couldn't trawl through anywhere near all that amount. Just to say that he was probably the best and most well-known scientist of the 19th century, which I found surprising when most people haven't even really heard of Lord Kelvin these days. But he was certainly the best known. There are monuments around Britain celebrating him and his life as well. And he was also an amazingly successful tech entrepreneur. So not only was he a brilliant scientist, he also made himself extremely wealthy, exploiting the patents and knowledge that he had. So we'll talk about some of those things during this lab. So let's sort of talk about his origin and his early life. So this is where he was born in rural Belfast. So Belfast hadn't started industrialization when he was born in 1824. It was very rural. This is you probably can't even see Belfast, but it's basically nestling as a little village almost in that estuary. So he's born near to Belfast, and his father is an amazing person in his own right. His father was basically a farm labourer, and there wasn't really much social mobility in those days. If you've ever read Thomas Hardy's Jude the Obscure, you'll know how painful it was for him that he could never make that social change from being a stonemason to something that he wanted to be. And so it was very hard to make mobility in social standing those days. But his father was an amazing self-driven man because he started life as a farm labourer. He taught himself mathematics, and he ended up becoming so eminent in mathematics. He ended up being elected the professor of mathematics at the University of Glasgow in 1832. And he went on to write textbooks in arithmetic, geometry, calculus, astronomy, and other ones as well, that a long time after his death. So his father himself was a self-driven and academic person. So they moved to Glasgow. Glasgow was not a rural place. Already it was in the throes of the rapid throes of industrialization. It was one of the biggest cities in Great Britain, and it was it was already very industrialized. Not always the healthiest of places to live in those environments. But one of the amazing things was that William Thomson, was enrolled in the university at the age of 10. I know they went to university young in those days, but that was really young. His older brother, I think, was nearly 12. So, okay, so he was a bit older. Um, so they were enrolled at university to study physics, basically, at the age of 10. I'm sure you'd all have loved to have been enrolled to study physics at the age of 10. But I think that must have been really annoying to have them in your class because even though they were that age, they won all the prizes. So they won the prizes for maths and for astronomy and for physics, and amazing. At that age, already his genius was being shown, even at that very young age. And then um, his education at the university is very classical. So they revered Isaac Newton, although he had died more than 200 years before. And they taught gravitation and mechanics from very classical textbooks like Principia and Laplace's Celestial Mechanics. But there was almost a life transforming uh, influence on Kelvin. At the age of 15, he was given this book, or almost by accident, he was given this book to read. Okay, it was in French, but Kelvin was already fluent in French, so that wasn't a problem for him. After all, he was already 15. We're all fluent in French by the time of 15, aren't we? And it was a rather big book, but it had a very profound impact. He said, I have become filled with the utmost admiration for the splendor and poetry of Fourier. I took Fourier out of the university library, and in a fortnight I had mastered it, gone right through it. Anyone here used Fourier transforms? Not too many. Okay, there. Oh, good. Yes, there's a few. Okay, it took me more than a fortnight to understand what the lecturers were talking about when they talked about Fourier transforms at university. But he had read this book, and this is some poetry. This is Fourier analytical theory of heat. Just poetry. Isn't it? Can you sort of feel the resonance of the poetry in your heart as you read this? It's amazing. But poetry to some people is not poetry at all, is it? So that's a poetry to Kelvin. And interestingly, it led to a great controversy. So Kelvin read this, Thomson read this, and Philip Kelland, who was the professor of mathematics, so a long number of years his senior, had published a book on the theory of heat in 1837. And in this book of theory of heat, he had said, uh, there can be little doubt that anyone who carefully examines the subject that nearly all of Mr. Fourier's theories in this branch are erroneous. So that's quite a bold statement. And Thomson strongly, I mean, really strongly, I think he was a bit apoplectic. He was really strongly disagreed with what Kelland had put in his book. And he wrote a paper at the age of 16. This is the first scientific paper to the Cambridge Mathematical Journal, proving that Kelland was wrong. He was a bit youthful and a bit abrasive in what he wrote. And apparently Kelland was sent the draft. So Kelland was rather upset when he read this paper. So it had to be toned down a bit. But when it eventually was published, Kelland had to declare himself that he was wrong and that young Thomson and, of course, Fourier were in the right. So that's an amazing thing to think that even before he had graduated, he was writing cutting edge scientific papers. So when he got to the age of 16, so when that paper was published, he went to Cambridge. So he didn't graduate from Glasgow University because if you graduated, you weren't in those days allowed to go to another university. So he went then to Peterhouse in Cambridge, and he was one of those people who was great at everything, as you'd expect. So he was winning rowing races. He bought his own boat and was winning rowing races. He helped found the Music Society, and the musical instruments he used at the Music Society, he also used in his lectures in later life to demonstrate acoustics as well. And he won the most advanced mathematics prize at Cambridge at the time, the Smith's Prize. And one of his examiners said to him, oh, to one of the others, said, "Oh, this guy is an absolute genius. You and I are only fit to mend his pens." And that's the examiners, who must have been very eminent professors in their own right at the time. And he published a number of scientific papers during his time at Cambridge. You got loads of time when you're university, you hardly have anything to do, so he just kept writing papers as well. And James Clerk Maxwell, who himself was a very eminent scientist, said that this paper particularly was one of the most valuable science-forming ideas because it was the first time in this paper someone had drawn the parallel between the transmission of heat through objects and electrostatics. And this paper then allowed the solving of a number of previously insoluble electrostatics problems because of the parallel that he had drawn between the two. So that was another very important paper that he published probably before he was the age of 18. And then he went to Paris. So he graduated ultimately from Cambridge, having had university education at the age of 10. So he'd been at university 11 years at the 1845. Now, there's a bit of background here I should tell you about. The professor of natural philosophy at Glasgow University was not very well. In fact, he was known that he was going to pass away probably in the next year or two of this date. And his father had his eye on this seat, and a bit of mercenary, I suppose. He's had this seat of natural philosophy at Glasgow University. So he said to his son, William Thomson, "William, keep your eye on this seat, but I think at the moment you're a bit too theoretical, although you're very good. Why don't you go and get some practical experience on the continent for a bit in a laboratory and learn how to do practical things?" And so he got some letters of introduction and he went to the continent and he went to spend time in the laboratory of Henri Regnault. I think that's how it's pronounced. That's what my French colleagues tell me. And he was also an eminent scientist in the Collège de France. And he was very well funded. He had a very well equipped laboratory for studying the efficiency of steam engines, the thermal properties of gases, and things like that. And um, young Kelvin, he really learned an enormous amount in that laboratory. He started really basically washing beakers, and in the end, he became a very invaluable laboratory assistant just in a few months. And he really acknowledged his debt to Regnault in 1900 after Regnault died. He said, "What I learned from him was a love of precision in all things and the highest virtue of an experimenter, patience." Now, I don't know if any of you have done experimental physics, but certainly in my laboratory, I know that when I was doing laboratory research a number of years ago, always seemed that it was ready to do the measurements when it was time to go home. I don't know why that was, but it always seemed that was when it was really. And you couldn't then go home, log onto the internet, and do the experiment from home like you can these days. You had to then stay and do the measurements. So he learned a lot of patience, as every experimenter needs to get the best out of it. But his practical experience paid off, and ultimately he was appointed Professor of Natural Philosophy at Glasgow University at the age of 22. Imagine that, at the age of 22, one of the most senior academics in the country at University of Glasgow. That's quite amazing, at 1846. One of the appointment panel said to his father, who's also, of course, an academic there, "It's plain from the testimonials that your son is or shortly will be the second Newton." And actually, he was known as the second Newton in some circles in the 19th century. And they were a bit worried, even though he'd had his practical experience, about his teaching ability, that it might be too mathematical and discursive. And indeed it was, but that didn't stop people loving what he did. And he really set about modernizing the department there. So I want to speak a little bit about his life as an academic teacher and modernizer now as he got to the university. So let's go back to the 1840s. The role of an academic was not to do research. That's maybe what you think an academic does these days on the whole, but the role of the academic was really focused on teaching his subject. They sometimes took private students, they sometimes wrote books, they sometimes gave public lectures, which you paid to go to. But that was all to supplement their academic income, which wasn't always that great. But Thomson just completely changed what it was to be an academic, the way he learned from the academics in France what it could be like, and he went set about changing academic life here in the Great Britain, really ultimately throughout the British Empire as well. He modernized the style of teaching. He established a teaching laboratory, which I'll talk about briefly, and he wrote a textbook, which was really the first new textbook known as Thomson and Tate, and I'll come to that a little while as well. So he used models to illustrate. If you go to the Hunterian Museum in Glasgow, there's a number of Kelvin models which he used to illustrate what he was trying to teach. But he had amazingly vivid illustrations. He used his gun. This is his gun, which was he used to be also like a National Guardsman as well in a regiment of some sort. And he had a gun that was his, and he used this gun to demonstrate the speed of a bullet. And so you can imagine filling out the health and safety forms that you have to do this. So this was packed lecture theatre, all these like 200 or 300 students, and he would load this gun with gunpowder, and then he would hammer the bullet down, and then he'd go on one knee, and he'd fire at this ballistic pendulum, which would probably be about 2 or 3 meters away. And the pendulum would move up, and from that moving up, you could then determine the speed of the bullet from its momentum. You can imagine the forms you'd have to fill in to do. Well, I don't think I'd probably have to relate to a bulletproof screen here before I'd be able to do it, wouldn't you? Just anyway, the students seem to love it. Anyway, kneeling on one knee and taking aim at the pendulum a few feet away and firing, the students cheered frantically before the smoke had cleared, and he was at the board doing the calculations. You can see all this in the Hunterian Museum in Glasgow. Interestingly, all the students of the university, including the arts ones, had to take natural philosophy. So it must have been a bit of a trial going to some of those lectures. For instance, one of the students said, I listened to the lectures on the pendulum for a month. Imagine that, sitting there for a whole month listening to those lectures. And all I knew about the pendulum at the end of the month was it bobbed. Because you can imagine it. Um, his enthusiasm was unstoppable. He wasn't interested in teaching what textbooks had in them. He only wanted to teach the new findings that were there. So he had no syllabus, one of his students says, of lectures. He had no notes. You can imagine having no notes, just standing up and talking, teaching natural philosophy, just like that off the cuff. Just must have been an amazing experience, if a bit distracted at times. He considered it unnecessary to teach what could be got from ordinary textbooks. So I think one thing about Kelvin, which really marked him out, was he wanted his teaching to be anchored in physical reality. I don't know if you've ever studied physics, but sometimes you go to a physics lecture, and I remember at university, you go to a physics lecture, the lecturer's given his lecture, and you've gone out and you think, well, yeah, but how's that relate to real life? Or even how's that relate to physical reality? So he did things like this. He said, he asked his students, for instance, what does dx by dt mean? And one of his students said, well, it means the limiting value of the ratio of the increment of x to the increment of t when the latter increment is indefinitely diminished. Of course, that's what it means. Everyone knows what that's what that sort of symbolism means. And of course, Kelvin said, don't be silly. That's what a mathematician would say. Doesn't anybody know it represents a velocity, dx by dt? He is so focused on anchoring the maths, and he was very mathematical at times, in the reality of the physics and the physical reality of the situation. So here's a picture from Nature in 1895, and this is his teaching laboratory. And it's amazing to think that there was no university physics laboratory before Kelvin established one in the 1840s. And even then, he had to beg to use an old wine cellar that wasn't being used to set it up. And the department got crazy because he kept spending money buying equipment to put in this laboratory, which they hadn't really got. But eventually, he won the arguments. And people loved it. The students loved it, and they went in their droves to go and teach and learn from him in the laboratory itself, because it wasn't just academic, it wasn't just in the head, it wasn't just on the blackboard. It was there in reality. You could do the physical experiments, you could see what was happening, and that was so important for understanding what was going on. I want to talk about this very famous book that he wrote very briefly. So in 1860, he was playing this game, curling, which never done, but he slipped and he nearly fractured his leg very badly, and he was in bed for a number of months, and he limped after that all his life because of the fracture that he got there. And he was visited by one of his friends, Peter Guthrie Tate, who was a professor of natural philosophy at Edinburgh, and they hatched this plan to write a new book in physics, natural philosophy. And Tate was driven to distraction by Thomson, because Thomson wanted this book to include everything new. And of course, everything new kept being discovered. So then he wanted to include that in there, and then that in there, and then that. And Tate was driven mad. But eventually, this treatise on natural philosophy appeared 7 years later in 1867, and it became known as the Principia of the 19th century, and most people refer to it, or most physicists refer to it, as T and T prime. And this is what it says in the preface. It says, so this is a picture from the MPL library copy of natural philosophy. Our object is to give a tolerably complete account of what is now known as natural philosophy in language adopted to the non-mathematical reader. We'll see whether that's true or not in a minute. Um, James Clerk Maxwell, we've already heard about him again. He said, Thomson and Tate, the two northern wizards, have brought together and made plain the findings of modern physics. Well, plain to some people, maybe, you'll see. When the students started reading it, they said, it's known in my year as the first glimpse of Hades. As it's, and you'll see why I said that as well. But it was sold widely. I mean, people bought it all over Europe and translated into many languages. So think, adapted in language adopted to the non-mathematical reader. So this is the non-mathematical reader. So I'm just wondering what it would look like if you'd adopted it for the mathematical reader. Maybe you wouldn't have bothered with the words. But this is just tip. You just turn the pages and it's full like this all the way through of equations. It's just an amazing book, but not really adopted for the non-mathematical reader. He had his own eccentricities. We all have eccentricities, don't he? One of his eccentricities was he carried these little green notebooks around, and here's a lovely picture of him from the Royal Society with one of the green notebooks. And when he started thinking about things, he used to pull the notebook out and just absent-mindedly carry on walking around and writing these things down. Vernon von Helmholtz, one of his friends, and also a very eminent German physicist, said he carried his green mathematical notebook with him, would begin to calculate in the midst of company, and is treated by awe, because they wondered what he was writing. I'm sure he wasn't writing down the chat that was going on in his notebook. There's a story of when he was at a dinner party with Queen Victoria, and obviously an idea came to him, and he was there trying to get his green notebook out. And his second wife didn't want him to do that, as you can imagine. Might be a bit rude to do that in the presence of the Queen. So she gave him a big kick under the table, which stopped him doing it. And that was a habit which he did for a bit till she broke him a bit of that habit, at least doing it in company anyway. He was there at Glasgow University for a very long period of time. He was there for 53 years as chair of natural philosophy. That's an amazing length of time, and an amazing transformation in science over that period as well. Interestingly, uh, at the dinner of his jubilee, he called himself a failure. And that's an amazing when you think about the things that he did, that he could call himself a failure. And that's because really he hadn't, there's a number of reasons why, but one I think is because he hadn't really understood the foundational foundation of why electromagnetism worked, those sorts of things, and because he hadn't done a unified theory of all of the known science that there was at the time, and that's why he called himself a failure. And Einstein, you could maybe called himself a failure for the same thing. Einstein, throughout his life, tried to develop a unified theory of all of science, bringing all the four forces of nature together, and he never succeeded. So if that's a failure, well, I wish I was a failure. like that as well, because it's just an amazing way to fail, isn't it? Here's a lovely picture of Kelvin. Is sitting in the middle, celebrating his jubilee in 1896. And here's a lovely picture of Kelvin, and I'm so pleased he hasn't stopped using equations, giving his last lecture in 1899. There he is, a wonderful picture. Anyway, he honours were heaped upon him. He was knighted in 1866 for his contribution to laying of the Atlantic cable. I'll speak briefly about that, and not very much because there's a talk next week about that. He was made Lord Kelvin in 1892. He was president of the Royal Society of Edinburgh twice, president of the Royal Society. He was one of the original members of the Order of Merit. He was a Privy Councillor. And he had numerous international awards heaped upon him as well. And he died in December 1907. Uh, where he lived in Largs came to a standstill. When his funeral happened in London, it came to a standstill. There were just for the crowd, absolute crowds of people. And he was interred in Westminster Abbey, next to or very close to Isaac Newton. And there's a window in Westminster Abbey celebrating his life. It just says, in memory of Baron Kelvin of Largs, engineer and natural philosopher. Wow, it's amazing, isn't it? It had a window. It was so eminent and so important in national life that they buried him in Westminster Abbey next to Isaac Newton, and they made a stained glass window to celebrate his life. Amazing. I want to say a few words about his personal life. It's a bit random, this, so just bear with me. Um, he was first of all married quite. He wasn't that old, and he got married to his second cousin, Margaret. Um, Poor Margaret was not a well person. She was fine when they got married, but very shortly afterwards, her health declined, even to the point where she couldn't even really move, and he had to carry her. And he was a very devoted husband. He had to carry her around the house to move her so she could move from one place to another. And they tried many things to improve her health, going to spas, going into Europe, going else, but nothing really improved her health, and she died. Sadly, she died in 1870. He was great friends with many of the great European scientists of the day. Again, here's Hermann von Helmholtz. He said Thomson, this is what he said on his first acquaintance with Thomson, but he became very great friends with him. He exceeds all the great men of science with whom I have made personal acquaintance in intelligence and lucidity and mobility of thought, so that I felt wooden beside him. And Hermann von Helmholtz was probably one of the most eminent scientists of the 19th century as well. So that's quite a thing to say of someone else. After his wife's death, he took up sailing. He didn't take it up by buying a little one-man boat, though. He bought this enormous schooner, which needed 18 people to actually manage it. He was very wealthy by that time. Okay, so he's very, very wealthy. You'll see how he became wealthy a little bit later. And here's a picture of him in 1870 trying out one of his depth gates. Yesterday I was in the lounge in the hotel, and I was just chatting to this person, and he had been a ship's captain, and he said to me, and I said to him, what I was giving a talk on Kelvin, and he said, "Really? I used to use a Kelvin device for measuring the sea depth, on the ship that I used to captain in the 1970s." Isn't that an amazing thing, though, that connection? Just meeting someone randomly like that, to have that connection just yesterday. And there's Kelvin using his depth device in 1870. And here's a picture of him and his second wife, Frances Anna, and his friends on his yacht in later life. Well, I'll tell you a little story about his second marriage, because that's quite interesting as well. So, one of the ways that Thomson made his money was laying telegraph cables. And he was laying a cable off Madeira, and there were some problems with laying this cable. And he ended up being delayed 16 days while the problem was fixed. And while he was there, he was invited by Madeira's um, wealthiest landowner, Charles Blandy. He was a landowner. He was a wine merchant. They're still there today. If you go to Madeira, there's Blandy's wine merchants still there today. And he had two daughters. And Thomson, and this is amazing. And so his daughter must have been genius in their own right. He taught them Morse code in 2 weeks. I don't think I could learn Morse code in 2 weeks. Maybe you could, but I certainly couldn't. Anyway, it seems that some sort of attachment developed between him and Frances Anna. And when Thomson was sailing out of Funchal Bay, she unfurled this blanket from her room, which said, and she had embroidered on in very big letters, which he could read, "Goodbye, goodbye, Sir William Thomson." It seems a bit forward, doesn't it? But anyway, that's what she did. Anyway, Thomson got it in his head that maybe there's something here, and so he sailed back in his. So that was with a business boat, but he sailed back in his own yacht in May the following year, and he used Morse code by flags uh, to say to Francis Anna from the harbour, "Will you marry me?" Isn't that amazing? And she Morse coded back with flags or whatever she had in her room, "I will." And and they got married in Funchal just a few weeks later. And my poor wife, I dragged her off to see the chapel where three times, I'm afraid, it was always shut, where Kelvin and she got married in the British Consular Chapel. This is a picture of it in Madeira, just before his 50th birthday. And if you do a Google search, you can find the actual records of his marriage. This is what it says. Church of England in Madeira, Register of Marriages. These are the marriage records of Sir William Thomson and Frances Anna Blandy, baptized in Madeira. So that's a nice little story about his second. So that led to a great change in his personal circumstances. He was very rich, I suppose he didn't really, in one sense, know what to do with all his money. He bought a yacht, but he had a lot more money as well. His wife was also very rich. She was an heiress. So do what you do. You build a castle. So he built a castle in Ayrshire coast near Log. This is a picture of that amazing castle. It had enormous grounds, very vast grounds. Had his own menagerie. I've seen pictures where they had camels and other things in the menagerie as well. And it's still there today. I saw an apartment recently advertised there for £120,000 if you're interested in living where Lord Kelvin lived. Here's a nice picture of Kelvin walking around the grounds with his notebooks, and inside the place as well is him, it's Helmholtz and his wife, and Francis as well. So quite a nice picture inside his castle there in Largs. And here's a picture of his very formidable wife. This is taken from the archive. I actually get the privilege of going into the archives of the Hunterian Museum, and they had this amazing, enormous picture of her in the archives there. I want to spend a bit of time speaking about his scientific achievements before I run out of time, so I should do that now. And there were some amazing things he did. He really invented the subject of thermodynamics, him and one or two other professors at Glasgow and in Europe as well, but he was really the one who drew it all together. He was the first person to really make a transatlantic cable work. He became a famous and rich person, as you'll see as well. And he really had an influence on establishing the place where I worked, the National Physical Laboratory. So I just want to say a few words about understanding temperature, because that's what I work on, so I should do really, shouldn't I? And so I just really want to think about it from the influences that were upon him. And I think why he could see further than maybe other people was because he had that influence from those French natural philosophers like Fourier and Regnault, was a wonderful experimentalist, and Carnot. I'll speak about Carnot briefly as well, and also Amintons as well. There was also some findings which the scientific establishment didn't accept of James Joule, which I'll also speak about as well, and the fact that there was many, many different temperature scales which puzzled him too. And by drawing all these things together, like a master craftsman, he stood on the shoulders of all these people and could see how it all joined together, and so invented thermodynamics. So Regnault drew together all his work into these massive volumes. Again, these are in the MPL library, and these are the sort of results that Kelvin used to invent thermodynamics. The French engineer Sadi Carnot was very influential in his thinking. What Carnot did, although he only ever published one book, and it was a small book, very hard to get at the time, it took Kelvin about 4 or 5 years before he got a copy. And really, Carnot's book talks about how a heat engine, that is a steam engine in those days, actually worked. And he was the first person to give a correct description of how a maximum possible efficiency engine worked. And that really helped Thomson in his thinking about how to put together our temperature scale, which in fact he called Carnot's little book an epoch-making gift to science. And then next week, in fact, in Paris, I'm not going to be there, but next week there's a week-long meeting celebrating the life and contributions of Carnot's life. And then there were massive number of temperature scales. Um, Kelvin was intrigued by this. Why are there so many temperature scales? Here's a thermometer from the University Museum in Utrecht, and there's 18 different scales on it. So why are there so many temperature scales? Surely there must be something more fundamental underlying all those scales. And then there was finally the findings of Joule. Now, Joule was basically a brewer from Manchester, but he was given uh, leave to do some by his employer to do some experimental work as well. And his experimental work, he showed that mechanical work, that is, this is like what he did. He had a small controlled vat of water that had paddles in, and by moving those paddles, the temperature of the water went up. At least that's what he found. And the scientific establishment just didn't believe him. They thought there was something wrong with what he was doing. Anyway, Joule and Kelvin met at this British Association science meeting in Oxford, 1847. And Joule was going to present his findings. He had a paper, and the presiding officer knew what Joule was going to say. And he said, "Oh, not that again. We don't believe that. Just summarize quickly, and then just let's move on to something more interesting and important." And Joule stood up and summarized briefly what he could, and that would have been it. But Thomson stood up and he said, "This work is of great interest." And all of a sudden, everyone turned around. Really? What's happening here? And that's because Thomson, by that time, although he'd only been professor a few years, had already become the foremost scientific authority of the age. And because he had that authority, people started saying, well, maybe what Joule found is important and right. And in fact, what Joule discovered, uh, incidentally, which other academics on France independently had discovered as well, the great principle of conservation of energy, which is a principle which we use widely today in physics. This is one of the pictures of his equipment that he used to discover that. Here's a handwritten manuscript by Kelvin. He had nice writing, didn't he? Which was one of the papers which talked about how to turn those ideas into temperature measurement. But then Kelvin, as it were, stood on the shoulders of all those people and drew them all together and said, well, the ideas were there is an absolute temperature scale, there's something fundamental underlying everything. Absolute zero, when molecular motion ceases, when there's no pressure really happens. Heat is molecular motion, which is very advanced because most scientists didn't think there were molecules till the 1900s. But he already felt there was molecular motion and that heat and mechanical energy are interconvertible, as there's conservation of energy. And by drawing these ideas together, Thomson developed thermodynamics. And the work that he did, we still use in gas-based thermometry today. If you read Hasek Chang's book, he gives into great detail about how Thomson went about that activity. But I want to move on about the transatlantic cable. Otherwise, I'm going to run out of time, I see. So Thomson became a global tech tycoon. Imagine a time when there was no communications, no way of communicating with America, and it took weeks to get messages one side to the other. So this company was formed, the Atlantic Telegraph Company, to bring a cable all the way from the south of Ireland when it was part of Great Britain. That's where they wanted it to Newfoundland. And Thomson was one of the directors. The original science director was not actually very good, and eventually he was sacked by the company. And Thomson became the science director. They hired this great ship, Isambard Kingdom Brunel's SS Great Britain, and they commissioned it to lay amazing thing, lay 3,200 kilometers of cable. No one knew how to make cable at that length in those days. They had to invent how to do it. But eventually, in 1866, after 10 years of really trying, they laid a successful cable. And it was an amazing. I'm not going to go into that, but basically, Kelvin invented all the science behind and then how to put it into practice in the laying of the cable. The Times said this is the most wonderful achievement of this victorious century. In modern money, it would have cost billions and billions to do that, to get it down and to get it working. But they soon made their money back. Queen Victoria knighted him and the other directors, and he became Sir William Thomson. And he became instantly recognisable. People recognised him in the street a day before, in the days before there were really pictures or photographs around. But he became instantly recognisable. He became a bit like the Elon Musk of the 19th century, but more than Elon Musk, because Elon Musk just takes technology that's around and turns it into products. Kelvin invented everything, then turned it into products. So that's quite an amazing thing that he did. Here's some of the equipment that he used. He invented and used for telegraphic communication. Again, from the Hunterian Museum, and he then became very, very rich through business partnerships. He held most of the patents for laying submarine cables, and they were exploited, and there were cables laid all over the world, all throughout the British Empire and everywhere. And he became very rich from that. He invented navigation aids like depth sounding, and he became very rich from that. And he invented many scientific instruments, and those scientific instruments really were used to support the emerging electrical industry. So he became very rich from that as well. So he became a very wealthy entrepreneur as well as a very eminent scientist. There's a lovely picture of the directors of the um, Kelvin bottomley and bed compass company. Here's the compass that became the standard of the British Navy. Because the problem, of course, was you have a compass needs to work on a wooden ship, and the British Navy then had iron ships. How do you get a compass to work? So Kelvin worked out the science of how to do that, and then patented the compass, and then sold the compass to the Navy, and it was the standard throughout the British Navy and others as well during his lifetime. Now, I haven't got very much time to speak about this, but Kelvin was very keen on reliable measurement. We saw that as he spoke about Renan. He really hated the imperial measurement system, and he ran it down whenever he could. It's littered throughout his writings how the imperial measurement system is such a rubbish measurement system. He said to this American audience that the imperial measurement system is a wicked, brain-destroying piece of bondage under which we suffer. So he was very keen to get rid of the imperial measurement system. The imperial measurement system, he wanted to replace it with a metric system, which really started in the 1791. But by the 1875, nearly 150 years ago, it had become global, and nearly all measurements are done in the metric system these days. The kilogram, the meter, the second ampere, the Kelvin, the candela, and them all. I haven't got time to talk about the SI system today. But Kelvin was so keen for the metric system to be adopted in Britain that he spoke and campaigned throughout the whole of the British Empire to get it adopted. In the House of Lords, when he was made Lord Kelvin, he said that the metric system be once legalised for all purposes. After 2 years, it be rendered compulsory by Act of Parliament, and the metric system be taught in all the public schools. That was in a speech he gave in the House of Lords in 1904. And he almost made it, actually. He almost made it. There was a bill drafted in 1910 for compulsory adoption of metric system, but unfortunately, he didn't quite live long enough to see it happen. And I think if he had lived just those few extra years, we would have been a metric before the First World War. But because he died, his great champion lost its advocate, and basically it wasn't until the 1970s that we became metric as well. I don't think Kelvin would have been very impressed by that. MPL, I'm looking at the time. I'm going to not talk really about MPL, just to say that MPL, where I work, is the home of measurement for the United Kingdom. It was opened in 1900, formally opened by the Prince of Wales in 1902. And when Kelvin responded to the Prince of Wales, he was given the responsibility to respond. He said, "The scientific importance of exceedingly minute and accurate measurements, though they may not strike the popular imagination, are the foundation of most brilliant discoveries." And I was at a talk in Hamburg last week, and this Nobel Prize winner, who I know quite well, Klaus von Klitzing, he talked about how he discovered the quantum Hall effect. And it's just exactly the same. Small and minute measurements, just knowing when it's significant. So on this curve on my right, if I do like that, there's just a wiggle. You can see the wiggle. And most people, I guess, lesser mortals would have thought there's a wiggle in the graph. Um, But von Klitzing realized that that wiggle was h over e squared, was a quantization of resistance. And from that, uh, he went on to win the Nobel Prize because no one had discovered that resistance being quantized before. And that became the foundation of electrical standards throughout the world. So it's an amazing discovery that he made by looking at minute observations, which most people would probably have ignored. So I'm just coming to the end of my talk. My chair will be very pleased to hear that. Kelvin saved the world at least twice. There's this science fiction book which is really terrible. I wouldn't recommend reading it unless you're really interested in things. But Thomas Edison and Lord Kelvin and others take the War of the Worlds and go to Mars and destroy the Martians so that the Earth is safe from a second Martian invasion. So that was kind of him, wasn't it, to do that? Um, this is actually a much more interesting book to read. Written in 1992, a steampunk novel. Anyone knows what steampunk is? I had to ask my wife what this was. Oh yes, good. There are some people who know what it is. It's sort of mixing science fiction and Victoriana. So it's a very interesting idea, and it's a really good read actually, uh, if a bit gothic at places. And in this book, Kelvin invents a time machine, and of course, time travel. Personally, I think time travel is impossible because a time machine breaks the second law of thermodynamics, which I found quite interesting in itself, because Kelvin would have turned in his grave if you thought you could break the second law of thermodynamics. But anyway, in the book, he does so. And then finally, really, I want to let you hear Lord Kelvin speak if this works. There's only one known recording of Lord Kelvin speaking, and I've been privileged to get permission to use it in this talk. Hopefully, it's going to work. I won't play it all because of the time, but you'll hear him speak. To work. There we go.
Chief action concerned in radioactivity is the shooting out of electrons from a non-electrified solid or liquid body. In the equilibrium of kinetic averages in any solid or liquid, every individual electron must occasionally have so high a velocity that it is shot out of the body. Hence, every solid or liquid body has something of radioactivity. The radium atom must, so far as we can at present judge, be assumed to have
Wonderful, isn't it? You could tell he's from Glasgow, I guess, from that voice. So,
one.
I've started. There you go. So I just come to the end of my talk. And I could have spoken all day about Lord Kelvin. I didn't speak anything about his contribution to electrical standards. I skipped over his contribution to MPL, but really, I think Kelvin had made really world-leading achievements in his life as a scientist, as an engineer, and as a statesman. And yet today, most people have never heard of. I often ask people, "Have you ever heard of Lord Kelvin?" People have never heard of him, and it's amazing, really, when he was such an important person in the 19th and early 20th century. And I think one of the reasons is he lived on that cusp between classical physics and modern physics. And although when you read his writings in later life, he saw radioactivity, he saw quantum mechanics, he saw relativity, he knew these were problems that needed to be solved. But the scientist you remember today isn't Kelvin, is it? The scientist today you remember is this gentleman. I met this gentleman on holiday a few weeks ago in Bern, and I thought I'll ask him. I'll ask him. So Albert, tell me, uh, uh, whose shoulders did you stand on? But he kept quiet. I don't know. I don't know what he was thinking, but I'm sure that Kelvin was one of them. You know, Kelvin's work shaped the modern world in which we live in today. Um, and I just wonder, when you look at all the things that he did, did he really fit it into that life that he had? I think it's about time Lord Kelvin appeared on this BBC program called Great Lives, don't you? What a great life he had. Any PhD students here? I think usually are a few. There's a wonderful maxim of Lord Kelvin which you really should take to heart. When you're face to face with a difficulty, you're up against a discovery. Ladies and gentlemen, Lord Kelvin, a great life. Thank you very much. I just want to give acknowledgements to many people who helped contribute to this talk. They were great, really, really good. It gave me complete freedom of access to the archives, the background, everything. I want to thank my wife as well for allowing me to drag her around various places, which maybe she would have gone if I hadn't wanted to investigate Lord Kelvin. I read lots. There's big stacks of book in my office at home, which I read as well. But there's lots to extra to read. Thank you very much.
Thank you, and we'll open the floor to some questions. If anyone has a question, stick your hand up. We'll get a microphone over to you, or also there's the Slido QR code. You can submit those online as well. Any questions?
There's one at the back.
Graham, thank you very much indeed for that. It was absolutely fascinating. Have any films been made about Lord Kelvin or others? Because I'm just sorry, not all others. Have any films been made or major documentaries? Because I must admit I haven't seen anything of that depth.
There are small ones you can find. The Institute of Physics, I think, has one, but not really a film, not a proper film of his life. But I think it would make a very interesting film if you leave out the equations. Though they in themselves are quite interesting, aren't they?
Any more questions? I think we had one over at the front.
There's one here as well.
Yeah, just a comment about adopting the metric system. When I was 8, I had to switch from using imperial to metric, and I complained to my granddad that I'd had to learn one system and then the other. And he said in 1914, when he started as an apprentice at David Brown Gears in Huddersfield, first day, learn metric.
Fantastic. I didn't know that. That's good to hear. I was 8 when they became metric as well.
We had another question here at the front as well.
There's 2. Oh, yeah, there.
It's only a tiny question, but it gives me the opportunity to just thank you for the amount of work you put in to giving us a talk. And to thank you for the amount of work you've put in, and I hope you can give that talk elsewhere. What was natural philosophy? That's my question.
Oh, yes. Okay. So first of all, to say yes, I am giving this talk elsewhere, and I've already given different versions of this talk. Yes, I've been very privileged to be given some money to actually prepare this talk by the MPL outreach. I would never be able to prepare it otherwise. So yes, so that was a real privilege. Natural philosophy is basically physics. It's basically physics. Yeah, yeah.
There was another question just behind there as well, I think. No.
Oh, there's one.
Just a little trivial bit of personal stuff. He didn't have any children. He was married twice, but no children.
No, well, that's yeah. So his first wife they were too ill to have. She was too ill to have children, and by the time he married his second wife, she was too old to have children. So all the money that he had must have gone to his vast number of nephews and nieces, because they were a large number of them. There was some controversy actually between his older brother, and himself, because his older brother became a Unitarian, and that actually impeded his academic career, his older brother. And William Thomson was a staunch Presbyterian, and that caused some friction as well between them. So I'm not quite sure whether that affected the inheritance as well. I don't know.
Thank you. Really excellent talk. Thank you very much. I seem to recall that Kelvin made some controversial statement towards the end of his life about closing the patent office because everything that had been invented, and there was unlikely to be anything useful in the future. Would you care to comment?
I can give comment on that. I have to say that some of the more outrageous things that Kelvin is attributed to have said, I can't find any record of him actually ever saying. So I think that he's been misquoted or misapplied. He did say some quite outrageous things as well. So he was invited a number of times to become the president of the Royal Aeronautical Society, and he used to write back dismissively, "Heavier than air flight will never happen." And of course, he was wrong on that. And at the end of the 19th century, he was very dismissive of radioactivity. He didn't really believe radioactivity happened or occurred, but of course, he changed his mind. What's amazing about Kelvin was he was a very humble person. Although he had very strong opinions, he was always willing to change his mind if the facts proved that his thinking was wrong. And that was certainly true over radioactivity later in life. And also, people say that he was very dismissive of things like relativity and things like that. But actually, he actually wrote a paper. I read a paper again later in life where he talked about his clouds, as it were, and there's some clouds on the horizon. And actually, the clouds on the horizon were quantum mechanics and relativity. But to him, he couldn't see. But Einstein stood on his shoulders and could see.
Any more questions? Okay, I think we'll close it off there. Just before we go, we do have the green air room at the top where Graham has offered to stay and have an informal conversation if anyone would like to follow up on anything. For as far as the next talk is concerned, not entirely sure. Is that still going ahead? Perfect. Yeah, so next talk, slight delay, but we'll still be going ahead. And just before you go, if I could ask you, there are some feedback forms dotted around. You can fill one out online as well. It really helps us make the festival better for next year and the rest of the events today. And thank you so much again,
Thank you.
Graham, for joining us.
Thank you.
Thank you.
And we should thank the volunteers, because without the volunteers, this festival would never happen. So thank you.